Hello, everyone. It's my pleasure to introduce my work to all of you. Today, my presentation title is Capacitated Electric Vehicle Routing Problem, and I'm Yinhao Qin. My supervisor is Dr. Jun Chen, and we are from Queen Mary University of London. I will introduce my work in the following 5 sections. They are introduction, literature review, approach, experiments, and conclusion. The first part, I will introduce the background. Nowadays, more and more people focus on electric vehicle logistics and transportation due to the environmental benefits of EV. But different from the vehicles with the traditional internal combustion engine, the EV brings its unique challenges like longer recharging duration, limited cruising range, a shortage of charging infrastructure. The CEVRP can be phrased as given a fleet of EVs, the goal is to determine the most efficient route for each vehicle, considering their battery charge and vehicle capacity constraints, so that they can begin and end their journeys at the depot when serving a group of customers. From this figure, we can see clearly the depot must be served once, and the charging station can be visited once, multiple times, or not at all. And the second section is our literature review. Regarding the approaches for solving EVRPs, there are three, which can be divided as three methods. The first one is exact methods. They are good at finding optimal solutions for small-scale instances, but the computational complexity is quite large. It will becomes impractical for large instances. And the second method is individual-based meta-heuristics. That means iteratively modify individual solutions. This method is quite efficient, but heavily depend on the local search and the perturbation methods. And as far as we know, the local search and the perturbation methods are problem specific and they are costly to develop. And the third method is population-based meta-heuristics. It usually maintain a diverse set of solutions concurrently, and it can be less likely to get trapped in local optima. Actually, that's what we used this method, population-based meta-heuristic. And the CVRP can be divided into two sub-problems. They are CVRP and FRVCP. CVRP, that means the capacitated vehicle routing problem. It only considers vehicle capacity constraint. And for FRVCP, that means fixed routing charging problem. It only considers battery charge constraint for fixed routes. And regarding the methods for solving CVRP, there are two directions. The first direction is the simultaneous optimization. That means it solves the routing and charging at the same time. And this method is effective. It can effectively address the coupling issue, but relatively increase the complexity. And for the second direction is the bilevel optimization. It means it iteratively solve the routing and the charging in an alternating fashion. This method reduces search space, but add a concern about the interaction between routing and the charging. And the first section is our approach. There are three different solution forms used in our approach. The first solution form is chromosome. It contains all of the customer's nodes, and it only contains customer nodes. Then is the second form is our upper levels of solution. It constitutes several routes, and for each route, it starts from the depot and the south side of customers, then go back to the depot. This sub-solution is capacity feasible, and after that is our lower level sub-solution, which satisfied the allergy constraint by inserting some charging station. And we use some upper level and the lower level optimization to make the transformation between these different solution forms. Then introduce our approach to CBMA. That means confidence-based Bilevel Memetic Algorithm. The workflow of it can be divided into two stages. The first one is the local optimization, and the second one is the reproduction. For the first stage, which can be shown in the green box, we can see in the beginning, it will select some individuals from the population pool and make the upper level optimization. Then we get our upper level sub-solutions, which are capacity feasible. Then we undergo our lower level optimization. We get our lower level solutions, which are allergy feasible. And in the meantime, we also use some filter strategies to select some promising sub-solutions for improving the efficiency. Then we get our locally optimized population pool. And in the second stage, that's our reproduction stage, which is consistent with the typical GA. It contains like population initialization, evaluation, selection, crossover, mutation, and iterate again and again until the stop criteria is met. Regarding the selection part, we design our own selection. That's the adaptive selection scheme. It will select some candidates from the population pool, from the locally optimized population pool and the immigrants for mating, for producing the next generation. This method, this adaptive selection scheme, can dynamically adjust the algorithm's convergence. That means it can accelerate the search in the early stage and maintain exploration capability as the search slows down. Then the fourth part is our experiments. We evaluated, our approach is evaluated on a quite popular benchmark set designed for IEEE WCCI-2020 competition for CEVRP. This benchmark set can be divided into 7 small size instances and 10 large scale instances. For the small scale instances, the customer size ranges from 21 to 100, and for the large scale instances, the customer size ranges from 142 to 1000. And there are some representative test cases. We can see the different distribution of these nodes. We made some experiments to compare our approach to CBMA and the state-of-the-art algorithms on 17 benchmark instances in terms of our objective value. Every approach is executed 20 times on each instance. For example, for the second column index, we get some information past the mean and the standard deviation. That's from our statistical results. And for the BKS, that means best long solution. And the best mean solution for the top performer are highlighted in bold. And the CBMA is our approach, and the gap calculates the percentage difference between CBMA and the BKS. Attention with the negative sign indicating our approach, CBMA outperforms the BKS. From this table, we get some conclusion. For the small scale instances, our approach is almost identical with BKS, and for the large scale instances, our approach is updated by the low 6 out of 10 large scale instances. And we also made a Friedman test. We rank these approaches, then we get our conclusion. Our approach, CBMA, performs the best. Regarding the convergence curves of these approaches on the large scale instances, the red curve, that's our approach CBMA on the instances x351, and on the instances from x573 to x916, it's clearly to say our approach CBMA is significantly better than other approaches in terms of efficiency and effectiveness. And on other instances, our approach is also competitive. Then we also compared the different selection scheme in our approach. We try to use the typical selection. We use the tolerant selection scheme. That's the blue curve in the figure. We can see it reaches the plateau in the early stage, which means premature issue. Then after we use our adaptive selection scheme, that's the red curve, it successfully addressed the premature issue. And we also wanted to validate the effectiveness of the component filter strategy. So we compared our approach CBMA and its counterpart without the confidence-based filter strategy. That's BMA in our table at a full convergence. Then we get since CBMA has not fully converged in instance x351 to x1000 when the termination condition is met. So for a fair comparison, we only compare the instances x143 and x214. Then we can see for the CBMA, it uses around 49,000 solutions for the upper level and the lower level optimization both. And for the BMA, it uses around 2,300,000 solutions. The ratio of them is around 2.1%. So the solution used for local optimization in CBMA is much less. And we can observe the similar phenomenon in the X214. Then we got the conclusion. This observation confirms that the confidence-based filter strategy indeed improves the algorithm efficiency. The last one is our conclusion. There are 2 points. The first one is our approach is top performing on the IEEE WCCI-2020 EVRP benchmark. It breaks the records of 6 previously best known solutions. The second one is we get an insight for maintaining a balance between exploration and exploitation. Thanks for listening, and feel free to ask if you have any questions.